ऑडियो वगैरह प्ले करने मिलेगा लगा दीजिए तुम्हें। हेलो अरे वो तो मिलेगा डायरेक्ट कुछ प्रॉब्लम और दिस ऑडियो स्पीकर लगा somebody connect speaker will just then is there hello sir am I audible Ganesh sir is muted now. Unmute पे है ना वो unmute sir I think you are on mute hello am I audible sir you connect hello okay it's a little bit clear not is your class hello you can change this also. Okay, yeah. Hello. Yeah. Recording कर रहे हैं. Yeah, and I need to present ना. हमने चालू किया था recording जो करेंगे. share access नहीं है इसमें. अच्छा okay. Present नहीं हो रहा. नहीं. Hello sir. Hello. Can I sir? Sir, do you not share the slides so we can just give the access for that? I'm back. Keep message interesting. Right, talking nonsense will maybe hello. No, it's audible actually. Oh, so the only thing is that I'm not able to save the screen. Access yeah. देखो is it
So you're audible and screen is visible also.
okay. Can you start? Can you just speak something soon? Hello, you're not audible to speak. Can I, sir? Hello, Karthik. Are you audible? I'm sorry, sir. Sir, give some please. Hi everyone, I am Madhu Kodecha and with me, Smita and Vicenta will present on subject selection for fine. So if we fine tune the model on a large data set, then it may happen that computationally it can be expensive and more time consuming. So the goal is to select the subset that is representative of entire data set, and after fine tuning the model
we get similar performance that finding the model with larger data set. So how to achieve this? There are many techniques through which we can achieve this. First one is diversity based by selecting diversity samples using uncertainty sampling like to select challenging example, then task specific to train the model on specific task. So first paper that we are going to present today is a sublinear data mixer strategy for instruction queuing smart. One of the author is Ganesh sir. So let's start with one quote. Your ability to juggle with many tasks will take you far. So if we place a model instead of the domain, then we can say, see that model is able to, if the model is able to perform on better on many tasks, then we can say that model is the best. So question arises that how many tasks we can select to train the model, which task to select and which task to avoid. After selecting the task, which subset of the data points to select and which to avoid, and how many samples to select for each task. So the data quantity and the task composition that matters the most. If we take an example of frame 22 that contains 1800 plus different tasks, and it is proven that by selecting 16 only 16 tasks out of this, uh, we can achieve similar performance by fine-tuning the model with only 16 tasks. So there are two questions that we need to answer: is how to select the budget for particular data set, and how to distribute among the tasks the budget that we selected. So let's jump to the subunit function. It is a set function that maps from the subset of finite set V to the reals with some diminishing return property. So the incremental gain that we get by adding an element in the smaller set is always greater than or equal to the incremental gain that we get by adding an element into the superset. So some of the important implications of subunit function in optimizing is like minimization of it gives the polynomial time algorithm, whereas the maximization of it gives the constant factor approximation algorithm. Many applications of sublinear function is variable feature selection, clustering, and more. And one of the main applications is data subset selection. So if we move further, then we can maximize the sublinear function with some constraint of cardinality, and we can extract a small and representative subset out of the big data set. But this problem can be complete. But luckily, one greedy algorithm exists that approximates this problem. That is, f of s greedy greater than or equal to 1 minus 1 over e into f of s star. So 1 minus 1 over e is approximately 63%. So the greedy algorithm, that is we will iterate over the budget times and select the maximum incremental gain for the element, and we will take the subset out of it, and also stores the gain for further calculation. So the main approach is divided into two stages. First is weighted task subset selection, and second is instant subset selection. So for first stage, we are using F1 subunit function and calculating the task that we are going to fine-tune the model, and also by using second order Taylor software function, we are calculating the weights for each and every task. So in the stage 2, we are actually selecting the samples out of the each task that we selected in the first stage, and making union of it to get all the samples. Yeah, actually, by doing the task entire task, we can we can avoid all those overlapping subset of the.
But then it could also go for sparse groups, right? Say I want weighted, uh, weighted set of instances. But the way it's in a sparse,
Mhm.
is there a difference between doing this? Yeah. So you know lasso,
Mhm.
right? Lasso
Mhm.
is a class. And you find a sparse set of weights in the regression. What's the difference between doing sparsity on the weights? L1 sparsity, also the values with us, but let's say L1 sparsity. What's the difference between sparsity of the weights and this approach into introducing effectively what is the difference? How does that effectively?
So actually, for here we are actually using our own budget to calculate the each and every distributing budget for each and every task. Whereas we are giving some more weightage to a particular task, and not equal weightage to all the tasks.
So you are saying basically that the budget component here, which may not be there in this class. I'm asking for specific difference. The difference is you are saying last one is no budget on the weights,
Mhm.
budget on the subset. Here there is an explicit budget.
Yeah.
Yeah, but I can always argue that in last one also I can put a constraint, L1 not
Yes.
less than equal to or L0 norm is
Yes. Mhm.
greater than equal to. But yeah, I mean, that is, please, again, that's one to to understand that question, right? What's the difference between solving one objective with sparsity versus solving, apparently there are two objectives.
Mhm.
In R max and this, but both are max on exercise and weights.
So for second approach, second stage, we are only selecting for instances from the task that we selected in first one,
Ah,
and not selecting for the rejected one.
the first case you're selecting weights
Hmm.
on tasks.
Yes,
The second one is selecting instances.
yes, and also reading the task that we redundancy or.
Now the weights are for the weights are actually for each instance or for the same weight share for all instances.
So our overall budget will be given at the first, and after that budget is divided across the tasks, all the tasks that we select first. So this is the algorithmic implementation of smart data research strategy, where we are encoding all the prompts and storing it to prompt embedding, and also calculating task embedding by averaging the prompt embedding, and after that we are finding task similarity between the all the tasks, and applying greedy algorithm on it to get task subset and gain for each and every task. Then we are using gain for getting the probability value by using Taylor's softmax function, and whatever probability distribution we are getting, we will then divide the budget according to that. And again, we are using cosine similarity to find similarity between the instance of a particular task, and applying greedy algorithm with F2 subordinate function to get instance out of that particular task, and making union of this to get overall subset. So choosing F1 and F2 subordinate function there are three main submodular functions. Yes. In first, yes, ma'am. So first one is facility location. Second is graph cut, and third one is slope determinant. So Sij here is a similarity value between ith and jth element, and facility location emphasizes on representation of the particular task, whereas graph cut balances representation and diversity among the tasks, and log determinant prioritize diversity among the tasks. So for experiment, data set used is plane 22, which contains plane 21, T0, and 2, a chain of stored data set, and diagram data set. Pre-trained model they are using is Llama 2, Falcon, and Mistral. For baseline comparison, they are using example proportional mixer and equal mixer. For evaluation purpose, they are using MMLU and Big Benchmark. This is the final result we are getting. And if we see with the weighted average of MMLE and Big Benchmark, BBH, then Smart is performing the best among the baselines. So this is the comparison with Plan 2 mixture of weights, which is proposed by Ron Platen. And Smart is performing the best with the budget of 50K or more. So if we see that by increasing task, exact match should increase. But here, an example of 128 tasks, it is decreasing. So selecting the number of tasks is also judicially picked. Here's the matrix to select the F1 and F2 submodular function. So for lower budget, log determinant is best for the F1 and F2. And by increasing the budget 50K or more, the GCFL page, graph cut, and facility locator is the best. So after the fine tuning the model, Mistral and Falcon, the Smart is performing the best with the budget of 2 lakh. This is the graphical representation of facility location and graph cut and log determinant. For graph cut and for log determinant. So how to select the task.
So now I'll be presenting this paper, Birthday Circuit Selection for Fine-Tuning Deep Learning Architectures and Resource Constraint Applications. This paper was published in IEEE. So as introduced by Madhav, fine-tuning pre-trained models would be computationally expensive. And this paper introduces Birthday Circuit Selection algorithm to fine-tune deep learning models efficiently. So this is their purpose statement. They have pre-trained the model M0, large set of training samples N, and their maximum allowable set size K. And their objective is to select a subset of K samples that maximize the generalization of the architect network on same task. So the key challenge is to how do we select the most useful and non-redundant samples. So this is their proposed framework where they introduce utility and diversity matrices to ensure the data informativeness and non-redundancy. They have presented 3 utility scores based on confidence, margin, and entropy. In fact, they have selected the entropy utility metrics because of its good performance and also the machine learning applications. To compute the diversity matrix T, where Dij would denote the diversity between sample xi and xj. They are using Gaussian kernel with parameter 1, and finally they formulate this problem as integer coordinate problem, and later relax it to linear programming problem for efficiency. So this is their final optimization problem where U is the utility vector that contains the utility source for the n training samples, and X is a vector which contains zeros and ones and has a binary constant of in its elements as 0 and 1, and the number of ones in X is equal to K, and lambda is the weight parameter given to the diversity metric. And due to the binary integer constants on X, you can actually combine U and D into a single matrix Q, where Q of Ij is lambda D Ij if I is not equal to J, and the diagonal elements would give the utility score for all the n examples. Yes.
Like, I mean, let's say the budget is of 5.
1 is 5.
Then it's 5. What do you think might happen?
Budget is 5.
And there's one instance repeated 5 times. Same example is repeated 5 times.
We will have to select like all the. Yeah, by then.
These 5 are only subset of the large number, of which one example has been repeated 5 times.
Okay.
And my budget for selection is 5.
Okay.
So, what is the problem with this formulation?
The diversity scores of the trainees examples are similar. Like it would be factored out with the diversity score.
One of those 5.
Yeah.
And so the point is, these algorithms, I mean, these formulations are susceptible to picking either all the 5 or none of them.
Yeah.
Because there's no cardinality constraint.
Yeah.
There's no, I mean, there's cardinality constraint of the X, I's. But yeah, but there's nothing like there's no such a selection favor than this is what the difference between the previous problem and potentially lies with one very important fact that such formulations in the case of redundancy might end up picking all the redundant examples or none of the redundant or random system redundant. You got my point?
Yeah. Yeah, this is their proposed circuit selection algorithm. So they take pre-trained model M0 and initial training set L, and they fine-tune M0 using L and compute their utility vector and diversity matrix D, and then they compute the matrix Q as described in the previous questions, and they derive the initial solution using the relaxed LP problem. And after this, X0 would contain the fractional values. So they do iterative concatenated round algorithm. So they compute xt dash using q vector and the previous xt minus 1 vector, and they select the top fractional values. And for those indices, they set xt to be 1 and the remaining elements to be 0. And they repeat this convergence algorithm until the solution converges. So, and after that, they fine-tune M0 using L and the selected subset. So, the data set that used is MNIST and state reverse numbers, CFAR, and the pre-trained models they have used is LexNet, GoogleNet, and ResNet. Baseline comparisons were random sampling, developmental point clusters, and some model optimization. The key matrices that they evaluated were accuracy and combination time. So they performed 90 experiments, in which random sampling achieves the highest accuracy only six times. They proposed to framework outperforms random sampling 67 out of 90 experiments, and typically achieves the best results and obtain the highest accuracy in 43 out of 90 experiments. And submodel sampling strategy achieves the highest accuracy in 16, while the proposed method achieves the highest accuracy in 25 experiments. Yes, sir, they mentioned the DPP.
It's a DPP and some other difference. DPP achieves 43, some other achieves 60. They are different approach.
Yeah.
And see, some DPP only one some every other some other.
Yeah.
So I think this is a very weak experiment. Then may take mixture of some other things.
So they proposed.
Yeah, we talk about what some other function.
No, sir. They proposed method depicts much better performance in random sampling, and its performance is comparable to degree in some hardware. And the main advantage of the proposed algorithm is in computation time. So the proposed method is computationally much more efficient than DPP and some modeling methods. For example, on the next dataset with election, DPP takes about 100 minutes to select a subset of size 1500, whereas the proposed method only takes 5 minutes. So this is the accuracy results on different data sets and 3 models. And this is the computational time result. So you can see that on the MNIST dataset with LXTech, the proposed algorithm has consistent runtime independent of subset size. So, for example, for subset size from 600 to 1500, the proposed algorithm is taking around 5.5 minutes for MNIST dataset with LXTech, while submodel is taking around 8.5 minutes.
So this is the third paper that we are presenting. This is a NeurIPS 2024 paper, small to large scalable data selection for fine-tuning LLMs by summarizing training loss trajectories of small models. So the introduction, the motivation remains the same. So LLMs perform well in general tasks, but they struggle in specialized domains. So to specialize the LLM for domain-specific tasks, we perform supervised fine-tuning, and the goal of data subset selection is to maximize the data efficiency in SFT by finding a subset of the SFT dataset that gives performance comparable to fine-tuning the model with full SFT dataset. So there are existing approaches like heuristic-based approaches, which include manual curation of the subset or using models such as GPT-4 for dataset evaluation, but they need specialized knowledge and it can get costly with large volumes of uncurated data. The second one is generating representations of each training example using a reference model and using metrics like the one stated on slide, perplexity, confidence, and hidden representations. But the disadvantage with them is that the metrics become less informative when there's a significant shift between the pre-training and SFT data. So as can be seen in the two figures, figure A and B, if the SFT and the pre-training data distributions aligned, it can give good representation that can be clustered. In the second one, the SFT data is math instruct data set. and it is different from the pre-trained Pythia 410M pre-training data. So it is not able to form good representations that can be clustered effectively. And the second challenge is that to get good representations, we need large models, and then that takes time to generate representations for each example. So the paper proposes a method called small to large, S2L. The idea behind it is that first, training loss trajectories are gathered for each training example using a small model, and then the trajectories are clustered, and then similar number of examples are selected from the clusters uniformly at random, which is then used to fine-tune the large model. So why do we form clusters of examples having similar loss trajectories? So the process is grounded in the theoretical findings of the paper that examples within the same cluster exhibit similar gradient during training, so they affect the model similarly. And the training dynamics of most examples are consistent across differently sized models of the same family. So as you can see in figure 3, it shows this for Pythia 70M and 2.8 billion models. So the examples that form clusters in the smaller model also form clusters in the bigger model, that 2.8 billion model. Yeah, and the figure 2 shows examples that in the same clusters have similar loss trajectories clustered together. And why is S2L effective? So for this, to check. So those examples will form in the same cluster, and then lesser number of samples will be picked from that cluster. They basically record the loss at each, like some.
And then use bucket.
Yeah.
Bucket.
Yes.
Okay. Unidirectional.
Oh yeah.
So it's a single dimensional
Yes.
feature space. There's only one dimension, right? Which is the loss.
Yes.
Or is multi-dimensional in terms of the loss at every step.
Yeah, so they record the loss at every step, and they fix like a trajectory length. So for example, 10, so they select 10 points to get the loss trajectories, and then they see the similarity. The second point, they show the clustering objective.
Okay, so this is something like disparity view. Disparity. And the distance is in the dimension of the trajectory space. So basically, you look at the loss trajectory for 10 steps. Those are so we have 10 dimensional vectors. Is that correct?
Yes.
You look at 10 steps, you have 10 dimensional vectors. And then you find the distance in that 10 dimensional vector space.
Yes. Yeah. So to check if each cluster formed by S2L predominantly contains a single topic, the fraction of the most common topic was calculated in each cluster, and the histogram shown on the slide was plotted, which also shows in orange the same for clusters from embeddings of a fully fine-tuned Phi2 model. So as it can be seen, most clusters formed by S2L using the Pythia 70 million model are based on a single topic and capture topic similarities more effectively than those from the 5 2 models embedding. So as it can be seen from the taller bars on the right end of the plot. So the orange one is the for the clusters formed by the 5 2 models embeddings. That is the fully fine-tuned model, and the blue one is for the lost trajectory clusters. So the problem formulation. So to adapt an LLM for a specialized domain of distribution D, we perform supervised fine-tuning with a domain-specific training dataset D-train that consists of prompt output pairs X and Y derived from the distribution D. And the conditional probability of producing sequence of output tokens Y given prompt tokens X is shown in the first equation. And the fine-tuning objective is given in the second equation, which is basically to minimize the negative log likelihood loss. And the data selection objective is that given a target language model P theta parameterized by theta and a fixed data budget capital B, that is maximum training examples to include in the subset, we find a subset S of D train of size B to train the target model such that it obtains a superior performance. So the methodology. So this shows the way loss trajectories are recorded for a training example I for a trajectory length capital T. So the loss of the proxy model, that is the small reference model, is recorded at T time instances. And next, K loss trajectory clusters are formed, C1 to Ck, such that cluster Ci contains all those data points whose loss trajectories are closest to the centroid of the loss trajectories in cluster Ci. Yeah, the small model that we use, I'm calling that as the reference. So the algorithm, given a training set D-train with their loss trajectories and budget capital B and the number of clusters to form K, we need subset S of D-train, which has size within the budget B. So the steps are like, first we initialize S to be an empty set and train a small proxy model and cluster examples in D-train based on the loss trajectories and sort them by size to get the cluster set C, which includes C1 to Ck. And for each cluster Ck in the cluster set, we calculate Rk, that is the number of examples to randomly sample from Ck. That is, Rk will be the remaining budget by the remaining clusters to process. And if the cluster size is smaller than the samples to pick, then we include the entire cluster since it's small. And otherwise, we sample from Ck uniformly at random Rk examples and include them in the subset. So we do that for each cluster and finally form the subset S. And these are two theorems that the paper provides theoretical proofs for. So the first theorem shows that examples with similar loss trajectories on the proxy model have similar gradients throughout the training of the target model. And the second is the corollary of theorem 1. So it shows that training with incremental gradient methods on the subset selected by S2L converges to a close neighborhood of the optimal solution found by training the larger model on the entire subset, on the entire data set. So these are so now coming to the experiments that were performed to validate S2L. So there were 6 baselines that were considered, which were open source data selection methods. So the baselines were random sampling, least confidence, middle perplexity, high learnability, and facility locations being the state-of-the-art models, state-of-the-art algorithms for data selection, subset selection, and confidence curriculum. So the domains that they performed experiment was First is the mathematical reasoning. So the data set used was math instruct data set, and the base models used were Pythia, Phi2, and Llama 2. And 6 evaluation data sets were used, out of which 3 were in domain, 3 were out of domain data sets. And the evaluation metric was exact match between the generated answer and the reference solution. And then coming to the experimental setup, the first setting was that the number of training steps were standardized to correspond to 3 epochs on the full data set. So there were 2 outcomes that were observed. First is that the state-of-the-art algorithms such as facility locations and high learnability failed when the data budget is too small, that is 30K, and their performance is decent with large enough data budget like 100K, whereas S12 stands out across data scales. So including the 30K, where it outperforms random sampling baseline when all others failed, and it consistently outperformed even full training across all data sizes. So as it can be seen in this figure 4, the pink one is the S12, so it outperformed all the baselines and the full data training. And secondly, data selected by S12 can transfer to larger models in different model families. So table 1 showed the result on the evaluation result on the 6 evaluation data sets for the target model Phi2. That was a 2.7 billion model using Pythia 70M small model. So the small model was used for the clustering the trajectories and selecting the subset. And the target model was Phi2. And figure 5 shows the comparison of time taken by facility location versus S2S. So for data selection, and as it can be seen, it is much lesser for S2L. Then the second setting was that the number of times each example can be seen was fixed. So it translated in smaller data sets into reduced training and storage costs. And the outcome was that using only 50% data, hence half the storage and training time, full data training performance was achieved. So it can be seen in the results in table 2. And the second domain that the experiments were performed on was clinical text summarization. That's it.
Yeah.
Yeah, the data selected by the smaller model will be used to fine tune the.
It doesn't matter.
Yeah. This was just the results for the second domain clinical text summarization. Yeah, so this is just the result, and there were 3 settings that were checked. So random sampling, so the 30K examples were randomly selected versus S2 selected samples in orange, and the full data was the third bar is shown. So even with only half the data, the model trained with S2 selected data achieved high, similar blue and significantly higher gel and BERT score compared to the models trained on the entire data. Yeah, that's it for the paper.
Yeah, sir.
That's a final problem.
Yeah, we would like to, yeah. So we'd like to propose our problem statement. So, yeah. So we'll be fine tuning an LLM on mainly math coding using budgeted subject selection. So our budgeted subselection algorithm would use utility score based on perplexity and chain of thought loss. This is to select hard and informative samples. And diversity score would be based on cosine similarity to avoid redundancy and ensure representation on different math problems. Yeah, so we'll be, yes. So we'll be focusing on 2 LLMs, Llama 3, 8 billion, and 24M0833, and our baseline comparison should be full fine tuning, random subset selection, DPP, and this hybrid approach, DPP plus utility based selection. So you first use DPP to remove redundancy and then filter the remaining set using utility score. This would be our methodology, and which I already told, and these are the references. Thank you.